here. Okay? So each one is going to have a piece of paper where all the beverages will be taken note on this piece of paper, and you pay for the whole bill at the restaurant. Okay? So it's a pleasure to start the second lecture by Sergei Popov, who is suffering from the flu, cold. Anyway.
Okay. Is it working? No? Really? Okay, I think it... do you hear me? Then that's okay. So, what we did yesterday, we considered simple random walk in ZD, and we did a simple calculation denoted by xn norm of Sn, where Sn is the simple random walk. What we did was expectation xn plus 1 minus xn given Sn is x was a certain constant, which is d minus 1 over 2d times 1 over norm x, or if you want times over 1 over xn, plus big O of x to minus 2, and the second moment of this increment was 1 over d plus big O of x minus 1. Well, I think it's x minus 2 here as well, but this way it's certainly okay, right? Next, I introduced something called Lampertis model or Lampertis problem. Lampertis process. It was a process x and in which lives in R plus, such that this expectation here xn plus 1 minus xn, given the history of the process up to time n, and also given that xn is equal to small x, is of order 1 over x, means some constant or even random variable over x plus terms of small order, and this square given was of constant order. Now, yesterday I wrote a stupid thing here. I denoted this by mu1 of x and this by mu2 of x, and of course you can You can do it only in the case when xn is a Markov chain, because otherwise it can depend not only on x but also on the whole history of the process. Nevertheless, I would like to write the same stupid thing again. Because although it's not correct to define it like this, but the correct definition, you have to write to define two things: mu bar and mu underline, which are essential supremum and infimum over this. Anyhow, the correct definition is here in the book and in chapter 3, and each time I see it, I get scared. So let's just do it this way, because anyway, in all applications, even if this guy here is not a Markov chain, we will see that you will always have a deterministic first term, and all the randomness will be here, okay, and all the randomness will be uniformly bounded. So it will be something uniformly bounded over some random variable, but which is uniformly bounded away from 0 and infinity over x squared, for example, as it happens in fact here. Because, well, you see, if you instead of putting Sn equal to x, you put xn equal to x here, then well, you know the norm of your walk, but you don't know where it really is. It may be in the point 5, 0, but it may be at the point 4, 3, and you have the same norm, but you will get slightly different thing here in this big O, but we don't care about it anyway. Okay, so let's just think that the main terms in these two expressions are deterministic. Okay. Now, let me state the result from kind of canonical classification of Lampertis processes. By the way, Lampertis process is something like this, and Lampertis problem means determine how does this thing behave. Okay. Theorem, it is 131 in the book. So, okay, it is formulated by for Markov chains because you cannot write something which is formally wrong in the book, but it holds for any adapted process modulo these comments that I just mentioned. So, if 2x mu1 of x plus mu2 of x is less than, if for all x large enough, less than minus epsilon, then the process is positive recurrent. Well, the process is positive recurrent means that the expected return time to a fixed interval of fixed domain around the origin is finite. Well, your process lives here. Here is the origin. You just fix some domain, some interval like this, in such a way that it is really possible for the process to go there. And then positive recurrent means that the expected time, starting from any initial position, the expected time of going here is finite. Okay. This means epsilon, if there exists some epsilon greater than or equal than 0, etc. Next. If absolute value of 2x, absolute value of mu1 of x is less than or equal to mu2 of x plus a big O of x2 minus epsilon, sorry, then it is null recurrent. Okay, again, if it's not a Markov chain, then a null recurrency means that from any initial position you will come back to this place around the origin with probability 1, but the expectation of the time that you need for this is infinite. Think of just simple symmetric random walk in dimension 1. And if 2x 1 of x minus mu2 of x is greater than epsilon, is uniformly bounded away from 0, then it is transient. Which means that, well, you start from here, and with probability, with positive probability, you will never return to this set around the origin. Well, okay, so you see, it's not really complete, but it's almost complete. So here, for positive recurrence and transience, we need that this should be uniformly negative or this should be uniformly positive. So for this to be uniformly negative, you have to have negative drift, okay, and with constant such that this term beats this term, okay. To be transient, you need that. Well, you need to have positive drift to the right, and such that this term beats this term. Now, what happens if they are asymptotic? Yes? Sorry? Well, I will comment on this now. So, if the thing just goes to zero, then you are in this kind of in this situation. So, we know that if you have this and this error term is polynomial, so you have these two terms are asymptotically equivalent and difference between them is polynomially small, then it is null recurrent. Well, then actually you can go further. Oops, sorry. Sorry. Now, if well, you can go further. You can ask, what if 2x mu1 of x, example is well, we have to distinguish two cases. So if this is negative, then you are kind of between positive recurrence and null recurrence. So if this is asymptotically equal to mu2 of x plus something small, then the answer depends on how big is, how small is something small. It turns out that the critical case is constant over log x. I'm only not sure if it should be plus or minus, but if you put the correct sign here, then you will have a phase transition in this constant. Again, if you put critical constant here, when you can add, I think, constant over log x, log x, and have a critical, have phase transition in this next constant. And then it is constant over log x, log x, log x, and so on. Can go up to. Yes, there is. You can formulate something integral terms, but some integral test. Yes, it is really perfectionism to the point, which is okay. Anyway, this result is already enough to prove the Polya's theorem. Just let's go back to this. So you see, for d equals to 1, what we have? We have mu1 of x is just 0 plus big O of x minus 2, and 2 of x is 1 plus big O x minus 1. Well, of course you don't need these big O's. I just insert to this so that in dimension 1 it's really 0 and 1. But formally you see that this holds, and so it's now recurrent. In dimension 2, well, everybody knows that simple random walk in dimension 2 is really, really critical. Okay, and in fact you see that mu1 of x is what is 1 over 4 times 1 over x plus big O of x minus 2. Mu2 of x is 1/2 plus big O x minus 1. And so you have exactly that 2x mu1 of x equals to mu2 of x plus a big O of x minus 1. So you have the exact equality like here, and fortunately the error term is small. And this permits us to conclude no recurrence. So these two cases are now. If d is greater or equal than 3, then, well, let me just rewrite. mu1 of x is d minus 1 over 2d. X minus 1 plus big O. mu2 of x is 1 over d plus smaller terms. So 2x mu1 of x is d minus 1 over d. So you should compare d minus 1 over d with 1 over d, which is mu2 of x. So, well, if you want transients, this term should beat this term, but you see that if d is at least 3, then d minus 1 is strictly greater than 1. So you conclude transients. Of the simple random walk. Okay. Now, I think I have to say something about how do we obtain such kind of results. Well, one more definition that everybody knows. So, suppose you have an adapted process. Fn is a filtration, increasing sequence of sigma algebras, and Xn is Fn measurable and integrable. So, if expectation of xn plus 1 minus xn given Fn is equal to 0 when you call this process martingale, if it is greater than or equal to 0, almost surely, then it's sub-martingale, and if it's less than or equal to 0, almost surely, then it's super-martingale. Okay. We also use in this book the word semi-martingale. Somebody knows what is semi-martingale? Oh, well, we don't know it either, but intuitively it is something that has to do with a sub, super, or martingales. So all these are semi-martingales, and also suppose that you have a process which is not martingale, but you can do something simple with it, and it becomes, let's say, super-martingale, and it's semi-martingale. Okay, so we like to have some broad term which means martingale and alike. Okay. Now I need to state some facts about martingales without proof. So, of course, there is a very, very rich theory about martingales, and in fact they are very useful. There is a paper by, I think, Yuval Perez with someone else called The Unreasonable Effectiveness of Martingales. It's it's similar to the paper called An Unreasonable Effectiveness of Mathematics by someone famous. Anyhow, sometimes you can do kind of magic with martingales. You know? But let me just state a few facts that we will use. So, Theorem 233 from the book. It's martingales and convexity. If Xn is a martingale and G is a convex function such that expectation of G of xn is finite, then G of xn is sub-martingale. Okay. In particular, if xn is martingale, then xn square is sub-martingale. And also, if xn is sub-martingale and G is non-decreasing and convex, and also you have this, then you have this. So when they need another fact which is called Martingale convergence theorem, I'm just writing the theorems from the book, but of course they are all classical. So if xn is sub-martingale such that sup in n expectation of positive part of xn is finite, then xn converges almost surely to some limit, and this limit is integrable. Okay. Also, there is, you know, this condition here sometimes can be difficult to verify, but there is an important special case where it's kind of automatic. Which is theorem 236 from the book. So suppose that xn is non-negative and it is a super martingale. Then then it's all you need, in the sense that xn converges almost surely to the limit, and expectation of this limit is less than or equal to expectation of the initial point. So you see, this is just the convergence part is just a corollary of this thing, because, well, if xn is super martingale, non-negative super martingale, then minus xn is non-positive sub-martingale. Now, non-positive means that this thing here is just 0, so this holds automatically. Now, now this part is just Fatou. It's just a Fatou lemma. Well, okay, so this will be, in fact, the really main tool of which will help us. Let me also formulate theorem 237, which is the optional stopping theorem. So suppose that sigma less than or equal to tau are stopping times. Okay, I did not define what is stopping time, but I guess everybody knows. Intuitively, stopping time is a random time such that when it happens, you know about it. When it happens, you know that it happened. Okay, it means that if the value of stopping time is n, then you know about it by looking at the first n steps of the process. Okay. Okay. Suppose that these are stopping times, and x tau. So this means minimum is uniformly integrable submartingale. Then expectation of x sigma is less than or equal to expectation of x tau is finite, and expectation and x sigma is less than or equal to conditional expectation of x tau, given all you know up to time sigma, almost surely. Now, you have this uniform integrability, which is sometimes not easy to verify directly. So there are basically three main cases where it holds. So corollary. It's 239. So suppose that Xn is submartingale, tau is a finite stopping time, and at least one of three following condition holds. So this is the logical OR, like where one is tau is less than some constant almost surely. 2 is absolute value of the stopped process is finite almost surely. And 3 is expected value of the stopping time is finite, and the jumps are uniformly bounded. Almost sure. When any of these conditions is enough for the uniform integrability, and so you can conclude that expectation of x tau is at least expectation of x0. And obviously, if xn is martingale, then you have this with equality. Okay, so it's useful to have in mind these 3 conditions because they imply uniform integrability kind of automatically. Okay. Now, the idea is use this to obtain some necessary and sufficient, well, to obtain some criteria for recurrence and transience of Markov chains. Theorem 252 from the book. So we have Markov chain, which is sorry, which is irreducible on countable state space and with discrete time. If and only if there exists a function, so f from this sigma is the state space and to R plus and finite and non-empty subset of the state space such that expectation f x n plus 1 minus f x n given x n equals to x is less than or equal to 0 for all x not in this finite set, and f of x goes to infinity as x goes to infinity. Okay. Well, I will not prove this implication. As, then the construction, if the Markov chain is recurrent, then you can always construct such a function with just a singleton, just one point, and well, but this construction will be a bit artificial. But instead, let me prove the sufficiency part, this implication. Well, consider the process yn equal to f of x n stopped at the first hit in time of A. What can you say about this process? It is a super martingale. It is a super martingale, and it is non-negative. So it converges according to this theorem. It converges to some limit, and the expectation of this limit is less than or equal to the expectation of the starting point. Now let me maybe use the part. So here is the state space, and here is the set A. Well, you can choose starting point x naught in such a way that f of x naught is f of x naught is bigger than f of y for all y from A. Since your f goes to infinity, you should, and A is finite, then you can do this. Now, this thing here should converge to some random variable y infinity, such that expectation of y infinity is less than or equal to this f of x naught. Now, if your Markov chain were not recurrent, this would not be possible, because, well, if it's not recurrent, it would be transient, and the then expectation of this would go to infinity as well, but you need that this must be true, you know. So the only way to have this is just go and stop in A almost surely. Okay. Is it clear? So again, if with positive probability you don't do this, then you will go away, and since your function goes to infinity, this y infinity would have an atom in infinity. And so you can't, you will not be able to have this. Okay. Okay, so this is a criterion for recurrence. Now, let me give a couple of examples. First, simple random walk in dimension 1. So let xn is just simple random walk in dimension 1. How do you prove recurrence using this theorem? Sorry? Absolute value. So f of x equals to absolute value of x. A is just the origin. Okay? So then for all x different from 0, you really have that expectation of xn f xn plus 1 minus f of xn given xn equals x is just 0. So you have this with equality. And that's all. This proves the recurrence of simple random walk in dimension 1. Now, how would you prove the recurrence of simple random walk in dimension 2 directly using this result? Well, so Sn simple random walk in dimension 2. So here it's a little bit more complicated. You take A equal to x from Z2 such that norm of x is less than some constant where this constant is big enough. And you take f of x equal to logarithm of norm x plus 1, well, because we need it to be well defined, to some power gamma, where gamma is less than 1. Well, so while logarithm, I think some people already understood from where did I take this logarithm. Now for the two-dimensional Brownian motion, well, in 2 dimensions, this function log of norm x in R2 is harmonic. So for two-dimensional Brownian motion, a logarithm of the norm would be martingale, would be a local martingale. Yeah, this is a good question. Let me finish with this, and I will comment on this. Okay. So, if you had a Brownian motion, then this would be a martingale. Unfortunately, when you start doing the calculations for simple random walk, the problem is that the simple random walk is not isotropic. So I think I always forget, but when you calculate it for x, which is on the axis, then I think you will get something. Okay, so on the diagonal, you will get something a little bit positive, and on the axis you will get something a little bit negative, or maybe vice versa. I don't remember. But the problem is that you won't get really 0. But, well, you will get something which is almost martingale, almost. And now let's recall this convexity result, which says that if you have a martingale and you have a concave function, then you get a super martingale. So this function, the power function with gamma less than 1, is concave. So maybe if you have a almost martingale, and then you take a concave function of it, then maybe you will get a super martingale. And it turns out that you really get a super martingale, at least outside a big disk. Right. So you can directly prove the recurrence of simple random walk in dimension 2 using this Lyapunov function. Now, let me answer Leandro's question. So how do you guess Lyapunov function? Well, you have to read the book. You have to see the examples and study them. And after that, you get some kind of intuition in such a way that when you see a concrete Markov chain, you want to prove recurrence, you think, okay, maybe this function will work. You start doing the calculations and it doesn't work. Then you get, okay, maybe another one will work. You start doing calculation, doesn't. then you say, okay, but maybe I can tweak it a little bit, and you tweak it a little bit, and it starts working. So it works this way. It's in Portuguese. I define it to students as a método de chutação científica. How do you translate this to English? Just scientific guess. I don't know. Guessing, yeah. It's really works this way. You develop some intuition about this, and then you start guessing. And if you are lucky, it works. Well, I think my time is over. Thank you for your attention. Das ist natürlich